So, good afternoon, and welcome to this Blue Sky project presentation. And I'm Daping Chu, I'm director of CAPE. And today we are very pleased that we have two Blue Sky project presentations. And they are from the Postdoc Blue Sky Acorn Award winners. The first presentation is on, let me get the numbers right. Is on the flexible and ultralight wireless power transfer system up to 1 kilowatt power rating with nanocrystalline flake ribbon. This project was awarded to Chaoqiang Jiang, Xinru Li, and David Gaona. And they are online, and Chaoqiang, I think this leaves to you.
Yep, thank you. And I will share my screen first.
Yes, please.
So please help me confirm if you can see my power slides.
Yes. Yeah, it comes.
Okay. Yep, thank you, thank you. Dear Professor Chu, our CAPE director, and everyone. Today, thanks so much for having me here to enjoy some very interesting result about the nanocrystalline flake ribbon. And today I'm going to show you the topic, the nanocrystalline flake ribbon for the power electronics. And we mainly have two applications. One is for the inductive power transfer. Actually, we can call it wireless power transfer. And the second one is the transformer. So first of all, I want to present great thanks for the support from the CAPE Acorn Blue Skies Research Award and also our group leader, Dr. Tan Long. And here is our outlines. And the first part, I will introduce what is and why we need wireless power transfer with the nanocrystalline flake ribbon. And the second one, I will introduce the flexible capacitor-less inductive power transfer system. And the third part will focus on the high energy efficiency for the transformer in high frequency power electronics. And the third part should be the Q&A. And so actually the wireless power transfer is very normal, or you can, everybody, maybe not everybody, a lot of people are using the wireless charger in your daily life. And here you can see previously we just used the cable charging, such like iPhone or your electrical vehicle car. And another side is about the wireless charging, right? So obviously you can say maybe if you use the cable charging, some dangerous or some risk will happen, and that's not so good to the human beings. And if we use the wireless power transfer, we can definitely, there is no contact, no physical contact, and also there will be no hazard to be electron. So we just for the cell phone, we just drop the phone and then charge. For the electrical vehicle, we just park and charge. And also we can do that, move and charge. So this is very convenient, and it can be completed automatic without any contact. This is super good. And the next one, this part is about the electrical vehicle wireless charger for the electrical vehicles, because currently we are doing the high power, high frequency charging for the electrical vehicle, but the power is very high. And if you use the very long and heavy cable to do that, maybe it's a very stuff for our human people, and also it's not nice, right? You just want to do everything automatic. So we propose the wireless charger for the electrical vehicle. So normally it should be, the power should be from the grid, and then we use the inverter, high frequency inverter to transfer the power from the grid to the transmitter coil, and then the transmitter coil will generate the alternating magnetic field and then picked up by the receiver side. So the receiver side will pick up the flux and then transfer to the electricity, and then charge to the battery. So this is very fundamental working conditions for that. And So this morning, I think our group member Yun Lei and Tim shared about the high frequency, high power inverters. But one of the core components is the magnetic core. So it's a carrier, energy carrier. So we call it energy carrier. So it actually are the transmitters coil and also the receiver coil. So they are generating and picking up the magnetic flux line and then charge the battery. But in these two coils, there is a very important component called magnetic core. It has been used to guide and also constrain the magnetic flux. So we can have a better coupling, we can have a higher transmission and efficiency. But such that this is the very basic topology for magnetic core. But previously, we just used the very conventional ferrite. Manganese, I think ferrite is very commonly used. And in our project, we proposed the new nanocrystalline ribbon. So what is the difference between these two materials? So you can see from this table. So actually, the first one is the saturation point, because for the conventional ferrite, the saturation point is very low. It means that at the same power operation, you need to have more, or you need to add more size to fulfill the same power operation. But for the nanocrystalline, the saturation point is quite high, almost triple of the ferrite. And also from the permeability, as a magnetic material, the permeability is very important. Of course, we want to have as high as we can have for the permeability. But if you have a higher permeability, the eddy current will be much higher. And also for the thermal performance, we can say that actually the nanocrystalline have higher Curie temperature. It means it will be more robust when it will be used under the high temperature. But there's one drawback about for the nanocrystalline is that the conductivity is not so good as the ferrite. So it means when you are using the high frequency operation, it means high frequency alternating magnetic field. So it will introduce high eddy current because the nanocrystalline is metal-based material, and then the conductivity is not so ideal, even not so good. So we must change it. So we use the laminated nanocrystalline ribbon. So actually for one piece of the nanocrystalline ribbon is only with maybe 18 micrometers. And then we use a lot of pieces, the ribbons to stack together. So after the stacking, maybe the stacking factor will be 78%. And then you can say from these figures, if we use the solid core, all solid core will be full of the eddy current path, so it will produce a lot of hot or heat. But if you use the laminated nanocrystalline ribbon, you can see that the eddy current is limited and also only happens in one surface along the nanocrystalline ribbon. And then each ribbon can be well isolated, so the eddy current loss can be hugely reduced. But at this time, we also want to increase the permeability. So we use the laminated, but this lamination will not reduce the permeability drop very huge, just a little bit decrease, but it hugely reduced the eddy current, but not hugely reduce the permeability. This is quite good. And so we built an experimental prototype to verify our idea, and we run the power up to 16 kilowatt. And if we use the ferrite, conventional ferrite, and it can be seen that actually the ferrite has been saturated, but for the nanocrystalline, it's still working very normal. And also we can find that if you use the nanocrystalline ribbon, and we can have a higher efficiency, such that for the DC conversion efficiency, we can reach up to almost over 95%. But for the ferrite, it's almost 93. I think maybe this is quite a huge improvement for the wireless charger. And also we need to consider the thermal performance. So because this nanocrystalline ribbon is the metal-based, so it has better capability about the heat generating and also the dissipation. So we can say that under the 6.6 kilowatt power operation, the ferrite, the temperature of the ferrite is not distributed very evenly, but for the nanocrystalline, the temperature is more even distributed, and also the temperature is a little bit lower. So it means the heat generation is lower than the ferrite. So this is mainly the two advantages of the nanocrystalline ribbon. And actually from the previous wireless EV charger, we noticed that we must use the compensation network. We call it compensation capacitor, to compensate reactive power for the IPT application, such like in these two figures. Normally we need to use the capacitor array, so it will occupy a lot of space, and also we need to use additional components. So we propose another one, is that we proposed a flexible capacitor-less for the medium power inductive power transfer application. So this is the topology. We integrated the capacitor and the inductor in the same coil, and this coil can be flexible, not because it's the flexible printed circuit, so it can be stretched a little bit. So we use the sandwich topology, and we have several layers. Each layer, such like the old layer, are connected together, and also the even layer are connected, and then they are insert with the under the topology like a sandwich, so we can have the straight capacitance and also the inductance together. We can have the self-resonant coil. So with this topology, we can have a very low resonant frequency, such like the 100 kilohertz. This frequency fulfills the SAE standard, so this frequency is good, and also the topology is more flexible. And also we built the prototype to verify that. We used 4 materials as the dielectric. So we use the nickel, and also we use the polypropylene, and also the polyimide, and also the fiberglass. And as a result, we found that actually the polypropylene performance is the best, and we can say actually the frequency is still very high, and also we can say that the resonant frequency is quite low. And because this is an integrated topology, so we can say that we have the magnetic field, and also we have the electric field. So we do a comparison to the conventional WTT coil with the compensation capacitor. So in terms of the magnetic field, there is no obvious difference between the conventional and also and the capacitor-free coil. But for the electric field, the proposed capacitor-free coil has obvious decrease, because the electric field is limited or constrained between the layers. So it means there will be less electric field linkage outside the space. And based on this topology, we are doing the incorporation about this flexible IPT system and the flexible flake nanocrystalline ribbon. Because previously we used the regular nanocrystalline ribbon as the magnetic core. It still has a little bit larger eddy current loss. So we propose another topology, the flake ribbon. What the flake means, there is a lot of gap between, there's a lot of gaps within one piece of the ribbon. So during the fabrication process, we use the crashing and compressing to generate some, it's not bubble, such like the air bubble, but filled with the polymer or some adhesive. And this is the final topology we propose that. So you can say that at each ribbon, there are still very tiny gap between the nanocrystalline pieces. So actually the eddy current flow path is further limited at a very small space. So if we can reduce the eddy current further. So we also found that actually for a lot of magnetic materials, they have different permeabilities. But for this nanocrystalline flake ribbon, we can feel the gap between the low permeability and the high permeability. So we are between these two, such like we have some soft magnetic composite. So for this one, actually the permeability is very low. So we propose the nanocrystalline flake ribbon to fulfill the gap between 500 to 3000, something like that. If we want to regulate the permeability, we just control the gap within one ribbon, and then we laminate them together to have a very flexible permeability and also the mechanical property. And we did some measurement to verify our topology, and it shows that actually for the flake ribbon, it does have better power density and also the energy efficiency. So as you can see, the regular ribbon actually will have more eddy current loss than the flake ribbon. So we use this flake ribbon as a transformer for the high frequency operation in a DAB topology, and this is the very basic topology. So after the measurement, we found that actually the flake ribbon can enjoy better energy efficiency. So actually the time is very limited, and I will go very quick about the result. And for the prototype and the result, we did a lot of some different power operations from high power to low power, and then we compared the energy efficiency. So from the left figure, we can say that actually the efficiency of the nanocrystalline flake ribbon is higher to 97%, and for the regular or for the ferrite, it is not so high to the nanocrystalline flake ribbon. So, and also we analyzed the core loss of the ferrite and also the nanocrystalline flake ribbon. So it shows that actually the nanocrystalline flake ribbon transfer can achieve 30% lower than the case using ferrite. So this is quite good for the high frequency operation, especially for the power electronics. And what is the drawbacks is that maybe we need to balance, because if you want to reduce more eddy current loss, you need to increase a little bit more space, and something like you will sacrifice the compact size to achieve better energy efficiency. And in summary, we developed and fabricated a novel material called nanocrystalline ribbon for the wireless charging, and also to further reduce the eddy current loss, we propose another topology. We insert some gap between the nanocrystalline to have the adhesive or some other polymer fillings. So this called nanocrystalline flake ribbon can be used to further reduce the eddy current loss. And for these two kinds of material, I think maybe these two will be the next generation material for wireless charging or some high frequency operation power electronics. And so I think this is my presentation about the nanocrystalline ribbon. And I think the result is very good for us to step into the industry application. And thanks so much for listening. Thank you.
Thank you very much, Chaoqiang. This is an impressive achievement with such a high efficiency on both the transformer and the DC-DC converter. Looks like your circuits, apart from transformer, the efficiency is nearly perfect. Yeah, the difference between transformer and the DC-DC converter is minimal. Yeah. Okay, so the presentation is now open to comments and questions. Chaoqiang, I have quick question. I think this is a very impressive progress achievement. How available is this nanocrystalline flake ribbon? Can it be scaled up now for industrial fabrications?
Yes. But if actually for this topology, there is no commercial product available in the market. But we redesign and we ask a factory to help us fabricate it. And because previously they are not sure if this topology is available for the industry application because they didn't have the practical data to verify that. And after our experimental test or some results, it shows that this topology did help to reduce the power loss. So maybe if we want to promote this material to the industry application, the fabrication will not be a big problem, I think.
Yes, maybe you should consider to do a spin out to try yourself. Yeah.
Yes, maybe later.
Yeah. Any other questions?
Yeah, I was going to ask. So you've demonstrated it for transformers. I wondered if you'd considered any other magnetic components that would be worth trying this as a magnetic coring.
Yeah, currently we just tried 2 applications. One is for the wireless power transfer because we need to use the magnetic core as the energy carrier, and another one is for the transformer. So Michael, you mentioned if any other, you mean material for the cores, right?
No, so it seems you've got a very good core material. I wondered if you were going to try and apply it to, say, inductors or chokes.
Oh yeah. So to be honest, we didn't try that as an inductor or a choke. We just tried for the wireless power transfer and also the transformer. But I think because the basic principle is the same, I think if we tried, we can still have the same result with high energy efficiency because we did help to reduce the eddy current loss comparing to the ferrite. Because the ferrite, the power loss of the ferrite is mainly from the hysteresis loss and the eddy current loss, right? But for the nanocrystalline, the eddy current loss will dominate it to the hysteresis loss. But actually we did to reduce the eddy current loss. So maybe if you want to apply it for the choke inductor or some other inductors, it will have the same effects, I think.
Okay. And do you think there's an upper frequency limit?
Yes, that's a very good question. So as you can see, our frequency is high, but not too high. Our operation frequency is around 100 kilohertz, right? So if you want to, apply this material to higher frequencies, such like megahertz or something, that will be, because the higher frequency you used, the higher eddy current loss you will have. So I think the nanocrystalline ribbon maybe is not so good for too high frequency operation. If you want to use something hundreds of kilohertz, that will be, so maybe there will be no obvious advantages.
Thanks.
Okay, let's thank the speaker again. Thank you very much.
Thank you.
Thank you, Professor Chu.
Now we move to the next talk. It is a Blue Sky Progress Report. So it's halfway through and is going to be given by Jenny Nian Jiang. And the title of her presentation is Exploiting Nonlinearity in III-Nitride Semiconductors for Full Spectrum Detection by Up-Converting IR and Down-Converting UV to Visible Light. Jenny, please.
Thank you very much, Professor Chu, for giving the introduction. I'm going to share my screen first.
Yeah, it's coming through.
Wonderful. So yes, I'm Jenny. I am a postdoc in Dr. Hannah Joyce's group. I joined in CAPE. I moved to England just before the first lockdown happened. So it has been a very interesting journey for me for the whole thing. And I really, really appreciate this opportunity, the Blue Sky Award, allow me to explore these quite wild and almost a bit crazy ideas. Yeah, so we are at the beginning of the idea, and even by the end of the Blue Sky Award, I'm sure there was still a lot more to explore than what we've shown. So the motivation of this project is actually, it came out with a very simple idea, thinking for these years, a lot of effort has been put into MEC detectors to detect the different part of the spectrum. A lot of effort has put in, and then how about instead of focusing on the detector, how about we can convert the spectra so that it can be detected by one state-of-art camera. So that was the original idea, and then I managed to put all my network, my collaborations together to come up with the whole project. So the background is the nonlinear conversion. Oh, sorry, I just need to turn on. I thought, sorry, I feel like my, oh, sorry, that's okay. So in the morning, Anna has actually talked a little bit about the nonlinear process, and it was first discovered in 1961 when they convert a longer wavelength to the shorter wavelength. And very recently, my collaborator in Australian National University has actually demonstrated that using a metal surface made of semiconductor nanostructures can actually efficiently enough to convert infrared light into the light that can be seen by our eyes. So it becomes the idea for making the night vision goggle as simple as our sunglasses. However, for the material that they're using, it suffers from one intrinsic problem, that the material they're using is gallium arsenide, which has a band gap that actually absorbs the resulted frequency light. So it affects the ultimate efficiency. So I moved to Cambridge to do research on gallium nitride, and I'm thinking, well, we have a new material. Can't we do that? Just change the material. So here comes the III-Nitride materials into the play. So for the nitride materials, they are very, these days they're very famous for the wide and tunable band gaps. So the wide band gap is desirable because we don't want the interested signals to be absorbed by our device. We want it to be detected by our eyes or other devices. However, this wide band gap is directly related with the property of that decided the nonlinearity, which means they actually have an intrinsically low nonlinearity compared to the narrow bandgap materials. So those are the things that we need to consider. And the other good thing about the natural materials is that these days the natural material has a really big and growing market. So getting this material is not, the material is already there in the market. So how are we going to overcome the very low nonlinearity of the III-Nitride materials? So in bulk materials, in general, even the one with strong intrinsic nonlinearity materials, the nonlinear susceptibility is low, as you can see, that minus quite something. And also it requires phase matching condition to achieve the frequency conversion, which actually largely restricted the conversion efficiency, and also it will restrict the wavelength that it can work with. So when we move to the nanostructures, it actually freed us from those limitations that is in the bulk material by having this local field enhancement, which also is known as mere resonances. And we also don't have such strict requirement in the phase match condition either. We have the flexibility in explore the size of the materials, the shape of materials, and the failing factor of the fractions of the materials impact on the nonlinear conversion efficiency. And it has already been reported in different types of nanostructures that orders of magnitude improvement in the conversion efficiency. And in 2014, this is also from my collaborators back in Australian National University, that they're actually able to convert a infrared source with the intensity of a table lamp to naked eye radiation by the third harmonic generation. So it's going to be a big project and it requires a lot of expertise here. So it requires expertise in understanding the gallium nitride growth so that we can get a good material. Because we want to explore different type of strategies of getting this material. So we also want to explore to get material, the planar structures, and then etch down, because this way we are having a lot more freedom in actually changing the shape that we want. Because if we grow the material always choose an energetically more preferable shape from the crystallography perspective. But if we done the etching, then it depends on, well, it can be controlled by the mask that we're using. And then we need to, ultimately the device, we want it to be flexible. So we want to transfer it away from the substrate we're using so that it can be attached to, for example, a lens. And then, of course, to do this, we need to do the structure characterization, and then we need expertise in nonlinear photonics design, and we need to measure all the performance of our nonlinear devices afterwards. And those are the I tap on my collaborators. So the original plan, which was thinking maybe the COVID wouldn't last for so long, that would allow me to travel, allow me to really engage with my collaborators, and it wouldn't take me so long to even just get access to the labs in the the Cambridge West Campus. So the original plan was we're gonna have 4 different type of work. So one is to develop the nanostructures, and then we need to go through simulations to find out the impact of the shape pattern and the crystal quality. And then we transfer the nanostructures, and then we do the performance. However, due to the restriction, I can only work on whatever I have away through the pandemic. So one job that I've done is to explore the gallium nitride growth. So I've been using the silent-assisted self-assembled growth. So compared to other nanostructure growth, this method requires no extra surface preparation for substrate. We don't need to add any extrinsic catalysts, which might pollute the reactor or the material. And also it offers a really fast growth rate compared to the typical gallium nitride planar structure growth. So typically it has 4 steps. From the beginning, we need to degas the surface of the sapphire, then we let the ammonia in at a high temperature to nitridate the surface of sapphire, and then we put in the precursors of gallium and ammonia in to promote the gallium nitride growth, and then we add silane to promote the growth on the desired direction. So with all the limitation of lab access and everything, I managed to find the growth window, which actually allow us to study the growth mechanism. So the gallium nitride growth is very sensitive to the growth condition. And as you can see, the growth window is very narrow, and they're so sensitive to temperature that even at such a high temperature, they're sensitive to about 10 degrees difference. So those are all the important information for us, because ultimately we would like to grow those material because those nanostructures compared to the planar structures, one of the great advantage is that the dislocation density is much lower in those materials. So to understand the growth mechanism, I've done trying to understand what's nucleation steps role over there. And we find out that this step is really critical. However, as soon as we have this step, it doesn't really introduce a lot of changes afterwards. which is something that we desire, because if it's ultra sensitive, maybe it'll make the whole thing more complicated. And to understand why this growth can be so fast, we did a bit of study on the surface for both the morphology and the chemistry study. So as we can see that the atomic steps are really clear on the sapphire substrate. However, after nitridation, those steps were not as clear anymore. And after nucleation, the interesting thing is we didn't really see any island structures as like gallium nitride. However, when we did the chemical analysis, we do find that there's still gallium left on the surface. However, they formed bonds with the aluminum nitride that is formed during the nitridation step, which tell us what's going on, the atomic structures on the surface, which formed the core of a screw dislocation, which when we study the after grown wires, we actually noticed that those dislocations becomes the nucleation site for all the layers for the growth along the growth direction. And the dislocation is also confirmed by transmission electron microscopes. So the next thing that we want to do is that once we have the structures on the substrate, we would like to peel it off to put it on a flexible substrate. So we have done the peel-off experiment, which with some really good preliminary results. So we embedded our nanowires in the C-parylene polymer, and then by simply mechanically peel the polymer layer off, it actually takes the nanowires in the polymer, as pointed out. So because of the polymer is not a good conductor and the gallium nitride is not a good conductor either, so the contrast is not very obvious, but if you look carefully, you can see those wires were embedded in the polymers already. And when we zoom in, you can actually see those wires exposed a little bit on the surface. We do also notice that very short ones, they still remain on the substrate. And then we do notice that the wires in the polymers were not holding the position as we wanted to. So there's still optimization that needs to be done, because ultimately we would like to transfer the structure with the pattern as we designed on the substrate. And by peeling it off, it shouldn't change the pattern. So there's still optimization work to do for this. So we also performed a preliminary simulation, and the results were beautiful, as you know, for a starting point. As we see, for the structures with a radius of 300 nanometers of gallium nitride pillars and height of 1 micrometers, and with a periodicity of 800 nanometers, we can already observe 3 resonance peaks over there. And this is just the preliminary results, and our plan was we will fabricate this structure and measure the nonlinear performance, and then based on the results, we will go back and further optimize this structure, because we can still improve the bonded states inside the gallium nitride nanopillars to further enhance the nonlinear conversion, thus increase the nonlinear conversion efficiency. So there's still a lot of work left, and now that the country is opening, labs are opening, the students has arrived. So I am very excited about what's going to happen next. So we will do gallium nitride etching. Our undergraduate student has started his project here already. We will move further in the device fabrications and optimize the peeling for the metal surface, and I will have a chance to visit my collaborators at last to actually further optimize the structures, and hopefully soon, and then get the structures to be measured, and then that will conclude the whole project. So I'd like to acknowledge my collaborators, because this is not persons. Sorry, can you still hear me?
Yeah.
Oh, wonderful.
because this is not one person's work. As you see, it actually requires expertise in different fields, and it involved quite a few different groups from Cambridge and from overseas. So I'd like to thank all of them for the support in this very difficult time to actually allow me to progress on this topic. Thank you very much.
Thank you very much, Jenny. And it is exciting to see such a crazy idea coming into terms. And also, I'm very impressed that you made progress on the material growth and patterning fabrication of the sample during such a pandemic period. I think the lab access has been very limited. So thank you for the hard work as well. And I do hope the pandemic situation will ease so you can travel, and Singapore, Australia will let you in. Yeah.
Yeah, so I was actually, when Peter mentioned earlier, says that, oh, you know, the lab only allows 2 people to get in like a few weeks ago, maybe a month or 2 ago. I was thinking, yeah, it make the training for me so difficult, because even I knew how to use the equipment, I couldn't get an induction. So that has been really difficult. But now I see the hope. I see the hope that I can finally get hands on all these things to make it happen. And I'm sure this is just the seed of something really big.
Yes.
Yeah, so I'm very excited.
Right. I think we'll leave the time for the questions and comments. Jenny, I just wondering, you said the next step you're going to do, and you're going to optimize in the NTU your structure and doing some measurements in the ANU. Yeah, looks like you have it very much planned. I'm wondering whether you will be there to be able to making new samples while you're traveling to there, because the optimization may be needed to get back to your original design.
Yeah, so that's the reason why I have to rely on so many people to work on different topics, because for me, I can only master one skill. So for the structure optimization, we have my PhD student, Ning, and the undergraduate student who just started. I'm really sorry that I still don't know how to pronounce your name if you're here. So it will really rely on different people's collaboration. We optimize different parts of the experiment, and then eventually when the optimized structure came out, we can just apply all the things that we have done, and then we get the results out. Because all the skills separately, they can work for different things. They're not necessarily just work for this. It actually works for their own projects as well. So it's kind of like tapping on everybody's expertise and trying to get everything work. And yeah, I have to admit that the restriction on traveling and the pandemic has making the whole process quite a lot more challenging than I thought it would be. I mean, it will be challenging anyway, but yes, it is a lot more challenging than without the pandemic.
Thank you. Any other comments or questions? Okay, if there isn't any more, and I think we wish you, Jenny, good luck with the rest of part of the project, and look forward to hear the final presentation probably in June next year. And
Yes.
Taking this time, I just would like to thank our speakers and thank all the audience here. And before we end, I would mention this, we have the CAPE Advanced Technology Lecture this month, and it's going to start at 1 p.m., which is about less than 15 minutes. And it's going to be given by Professor Tero Oyampela, and he was the former CTO of Nokia. And the title of his lecture is Platform Tech Strategy, How to Win with the Platforms. So there is a Zoom link on the CAPE website, which you can follow, and also on the flyers. So now, thank you, everybody, and hope to see you next time. Thank you.
Thank you.
Bye-bye.
Bye, everyone.
Bye-bye.
Right, we're going to move on to the next platform, yeah? Yeah,
Yes.
in about 10 minutes. Yeah, I think it's very nice to see presentations here, the progress they are making in such a difficult time. Yeah.
Definitely.
Yeah. Anyway, okay.
See you soon.
So, thank you, Denise. I hope the recording works this time. Yeah.
It does, yeah. It just takes a little time to convert.
Okay.
Yeah.
Yeah, it did take time. Yeah. Particularly long videos. Yeah.
Yeah.
Okay.
See you
Okay.
soon.
See you. Bye.